everyone. Today we are beginning Unit 8, Triangle Similarity. We will have a few proofs where we are proving that triangles are similar, and that will be coming in some later sections, but today we are looking at Section 1, which is Rates, Ratios, and Similarity in Polygons. So to start with, we have a ratio. A ratio compares two numbers by division, and we typically write ratios in three ways. It'll be an A to B in words, A colon B, and A over B as a fraction. So these are the three different forms that ratios come in. And here's a fun real-life example. We have the mullet. The mullet is a haircut that actually is balanced by a ratio, which is a 17 to 9 ratio is what they're giving as our example here, or the ratio of party in the front to the business in the back is what they're looking at, which used to be an old thing, but that's been coming back lately. All right, so example 1, let's take a look at some numerical ratios here. It says give 3 equivalent ratios to the ones provided below. So if you have an equivalent ratio, and I'm actually going to back up here a second because I just remembered I forgot to write this in here. So we have these formats of ratios, but all of these are on the condition that B is not equal to 0. So you can't have your B as 0. So this is on the condition that B does not equal 0. All right, so back to the equivalent ratios. An equivalent ratio is a ratio that is going to have the same overall value. So we can get an equivalent ratio by multiplying each piece of our fraction by the same number. So a 1 to 2 ratio, 1 times 2 is 2, 2 times 2 is 4. A 1 to 2 ratio will be the same as a 2 to 4 ratio, or the same as a 4 to 8 ratio, or the same as an 8 to 16 ratio. All three of those are examples of equivalent ratios. They all have the same overall value. We can do that with this format as well. So a 7 to 9 will be the same as a 14 to 18, or a 21 to 27, or we could continue. Same thing here, and you should have 3 because it asks for 3, but we have our point. Same thing with this type of ratio. If it's a 5 to 3, then an equivalent ratio could be 15 to 9, or 10 to 6. Then you would need a third. All right, example 2. This one is taking a story problem and applying a ratio to solve it. So it says, suppose there are 600 students in our school. Use the ratio of boys to girls in our classroom to estimate the number of girls, which we're saying is 4, and boys, 15, in our school. And this data is actually from one of my current classes, and there are about 600 students in our school, so this will be fairly similar to what we have at WAMA. So I have 4 girls, I have 15 boys, which means that I have a total of 19 students in this specific class. In our class. So if I take the sum of these two things, 4 plus 5 is 19, and I find out how much we'd have to grow between our 19 students in our class and the 600 students in the school, we can use that to figure out how many girls and how many boys we would have. So I have 600 divided by 19, which is about 31.6. So now I can take that 31.6 and I can scale the number of girls and the number of boys. So I have 4 times 31.6, and I have 15 times 31.6, and the answers to those will give us an estimate for the number of girls and boys in our school. So I have 4 times 31.6, which is well, we have 126.4, which will take care of the decimal in a second. And then I have 15 times 31.6, which is 474. So in our school, there is approximately 100 and we'll say 27 because you can't have 0.4 of a person, 127 girls and approximately 474, that should be on 127, 474 boys. That's our best estimate using the fact that there's 19 students in our class, 4 of them are girls and 15 of them are boys. There is another way to solve this using cross products, and we'll come to that in a little bit, so we'll come back to that. Example 3, we have the ratio of the side lengths of a quadrilateral is 2 to 3 to 5 to 7, and its perimeter is 85 feet. What is the length of the longest side? So what we need to recognize here is that if we have a ratio of 2 to 3 to 5 to 7, we don't know exactly how long any of these legs are. So my ratio is going based on some unknown number. So I take that unknown number and I'm going to plug it in. So I have 2x plus 3x plus 5x plus 7x. And this is all going to add up to 85 feet. And I know that it will be 85 feet because it says that the perimeter is 85 feet. And we find perimeter by adding the side lengths together. So I have the 2, 3, 5, and 7. I'm going to add these together. 7 plus 3 is 10, plus 5 is 15, plus 2 is 17. So I have 17x is equal to 85 feet. Going to divide out 17, which leaves me with x is equal to 5. So now I know my missing piece, but that doesn't tell me the length of my longest side. To find the length of the longest side, I need to take the ratio of the longest side, that's 7x, and we need to plug our x in. So I have 7 times 5, which is equal to 35. So the length of the longest side is 35 feet, and that is our final answer. All right, so we had one where we needed to take a small portion and calculate for a large whole, and then we had another piece where we knew the ratios between the sides and what they were added together, and we calculated for a small piece from that. So now that we've looked at a couple examples using ratios, we can solve with ratios using what we call a proportion. And a proportion is an equation stating that two ratios are equal. So an example of a proportion would be something like 1 to 2 is equal to 2 to 4. 1/2 is equal to 2/4 as fractions. 1 to 2 is equal to 2 to 4. That would be a proportion. And the cross product property states that when we multiply the diagonals of a proportion, it gives an equal statement. So if I were to multiply 1 times 4, which equals 4, that should be the same as multiplying along the other diagonals. 2 times 2 is equal to 4. 4 is equal to 4. It is a true proportion because those cross products are equal. So if we flip to the next page, there's an example where we want to know, let's jump to example 5. Are these proportions equal? And to find that out, we're going to multiply across the cross products. So I have 3 times 63. 3 times 63 is equal to 189. And 27 times 7. 27 times 7 is equal to 189 as well. So this checks out. Those proportions are equal. So I always do my proportions, my cross products, using arrows like this, but I know a lot of people call this the butterfly method and they circle instead. That is a valid option. We'll do that over here. So I have 5 times 14, which is equal to 70. And then I have 2 times 30, which is equal to 60. 70 is not equal to 60, so this is not a proportion. So this is no, not a proportion, because they are not equivalent. And this one is yes, and it is a proportion. Those are my answers. We have the ability to check if a proportion is true, but we also have the ability to make a proportion be true if we solve for a missing piece. So that's what example 4 is looking at. So we have 3 to 15 is equal to x to 45, and we have to figure out what we can plug in for x to make this true. And there's a couple options. If you can figure out what the difference between 15 and 45 is, you can apply that up here and then multiply 3 by that same number. But we don't have to do that, and there's no guessing and checking using the cross products. So if I multiply across my fractions, so I have 3 times 45, which gives me 135, and x times 15, that leaves me with 15x. So now I know that I have an equation to solve for with x. So I'm going to divide out 15 from both sides, which leaves me with x is equal to 9. So x has to be 9 to make these proportions true. All right, so now that we've looked at proportions and ratios in general, we can use those to solve for missing pieces in similar shapes. So previously we learned that two shapes can be congruent, meaning that they have the same size and same shape, and the symbol we used for that was right here. It's an equal sign with a tilde on top of it. Now we're looking at shapes that are similar, meaning that they have the same shape but not necessarily the same size. And the symbol we use for this is just the tilde. So things are similar if it has a squiggle between them. So an example of some similar shapes would be these triangles. They have the same shape, but the size is very clearly not the same. And we have, again, same shape, different size. So two shapes are considered similar if and only if their corresponding angles are equivalent and their corresponding sides are proportional. So angles have to be the same, and side lengths all have to be to scale. So if this side length is half the length of this side length, then this has to be half of this. Our right side has to be half of this larger right side, and the top side would have to be half of the top side of our corresponding shape. Lastly, a similarity ratio is the ratio of the lengths of the corresponding sides of the two polygons. So if we look at these shapes here, a similarity ratio, it gives us is 1/2, and we find that by taking our we find that by taking one side and setting it on top of its corresponding side. 4 to 8 is the same as 1 to 2, so there is a 1 to 2 ratio. And that's a similarity ratio, specifically because it is between corresponding sides of similar shapes. All right, so let's take a look at some examples. Example 1, explain why the two triangles below are similar and identify their similarity ratio. So if we zoom in on these triangles here, we have 60, 60, 80, 80, 40, 40. Those triangles all have the same angles. That checks one of our requirements. Shapes have to have the same angles. Next, we have to check to see if these have corresponding sides or the same similarity ratio between the sides. So if I have 28 over 14, that is equal to 2 to 1. I have 18 over 9, which is also 2 to 1. And then we have 24 over 12, which is also 2 to 1. So these triangles are similar because they all have that same 2 to 1 ratio between the sides, so our side lengths are proportional and our angles are congruent. So we're going to say the triangles are similar because all sets of corresponding angles are congruent, and all sets of corresponding sides have the same similarity ratio of 2 to 1. And that is our response, this paragraph here. Well, sentence. That's our answer. So we had to do all of this work, checking all the angles, checking all the sides, in order to come up with our answer of are they similar or not. All right, example 2 is a different situation where we already know that the triangles are similar, and now we need to find missing pieces. So I can solve for the missing angles fairly quickly because we know that the angles are corresponding, and because we already know that these shapes. I can solve for the angles rather quickly because we already know that similar shapes have to have the same angle measures between corresponding angles. So angle L is 80, so angle R also has to be 80. So R is 80 degrees, and I'm going to write that down here as well. And then M would have to be 60. Now we need to figure out our missing side length, which is only this one right here. So we need to find the length of PQ. And we can do that a few different ways. I'm going to solve for this one using cross products. So I have some unknown length of PQ to any other side here will be good. So I'm going to pick this 3 centimeters here. So RQ is 3. I just have to make sure that I use the same corresponding ones. So I have PQ, which is between 60 and 40. Between 60 and 40, it will be 10 on our larger shape. And then between 60 and 80 would be 6 for LM. Now I'm going to solve for this cross product. 10 times 3 is 30. PQ times 6 gives me 6 times, PQ is just our variable, so you could use X in place if you would prefer. So that's what's happening there. And I'm going to divide out that 6, which means that our missing side of PQ is equal to 5. And I will switch this to be PQ so that it's clear. All right, so our missing side length, our length of PQ is 5 centimeters. And those are all the 3 missing pieces that we have in this shape, and we are able to find them all. All right, this is where we're going to stop for today. We'll pick back up with section 2, which is where we're going to begin working with our triangle similarity proofs.